Welcome to Gonit Guru. Today we begin our journey with the first chapter, Number System.
Sir, haven't we already learned about numbers before?
Yes, but now we'll explore all kinds of numbers in depth, from natural to real numbers. We start with the simplest, natural numbers. These are numbers we use for counting.
So 1, 2, 3, 4 and so on.
Exactly. When we include 0, the set becomes whole numbers.
So whole numbers are 0, 1, 2, 3, 4 and so on.
Perfect. Now let's include negative numbers. That gives us integers, denoted as capital Z.
So integers go like -3, -2, -1, 0, 1, 2, 3 and so on.
Exactly, integers cover both sides of 0, from -infinity to +infinity, a number that can be written as p by q form, where q not equal to 0 is a rational number.
So 1 by 2, -3 by 4, even 5 are rational number, right?
Yes, because 5 can be written as 5 by 1. But some numbers can't be written as p by q form. Those are irrational numbers.
Like √2 or pi?
Exactly. Their decimals never end or never repeat. When we combine rational and irrational numbers, we get real numbers, which are denoted as capital R.
So every point on the number line is a real number?
Absolutely. 1 by 2 is equal to 0.5, which is terminating, whereas 1 by 3 is equal to 0.3333, and so on. A non-terminating repeating.
And in irrational numbers don't repeat or end, right?
Exactly.
Teacher, can you show how can we represent √2 on a number line?
Sure. Let's see to understand this concept. Having the knowledge of the Pythagoras theorem is very important. Let us take side AB. Now we draw a perpendicular from it side BC, both of 1 unit each. Here we will obtain the length of AC as square root of 2. With the help of this concept, we can easily draw square root of 2 on the number line. This is a number line. We take this distance as 1 unit, as well as this distance as 1 unit. Now the length of this segment will be the square root of 2 with the help of a compass. We draw the same length on the number line, and we will obtain the total length as square root of 2. Similarly, we can draw the square root of 3 on the number line. Now let us discuss some of the algebraic properties of real numbers. The main properties of real numbers are closure, commutative, associative, distributive, identity, and inverse properties, which describe how they behave under addition and multiplication. Closure means the sum or product of two real numbers is a real number. The commutative, associative, and distributive properties relate to the order and grouping of numbers in operations. The identity and inverse properties involve the additive identity 0 and multiplicative identity 1 and their corresponding inverses. Let's talk about the properties of real numbers. The first one is the commutative property of addition. For any real numbers a and b, a plus b equals b plus a. So, when adding two numbers, if we change the order, we still get the same result. For example, 2 plus 3 is the same as 3 plus 2. Next is the commutative property of multiplication. A times b equals to b times a. So, just like with the addition, even a product, we change the order, the result will be the same. For example, 4 times 5 is the same as 5 times 4. Next, we have the associative property of addition for any real numbers, a, b, and c, the quantity, a plus b plus c equals a plus, the quantity, b plus c. So, if in a sum, we change the grouping, we still get the same result. For example, the sum of 37 and 95 plus 5 equals 37 plus the sum of 95 and 5. So, we change the grouping. However, the result is the same. And as you see in this example, when adding these three numbers, it is more convenient to add 95 and 5 first, then add 37. Next is the associative property of multiplication, the quantity. A times b times c equals a times the quantity, b times c. So, if in a product we change the grouping, the result will still be the same. For example, the product of 83 and 25 multiplied by 4 is the same as 83 multiplied by the product of 25 and 4. So whenever convenient, we can change the grouping and still get the same result. And in this case, it is more convenient to multiply 25 and 4 first, then multiply the result by 83. Next, we have the distributive property at times the quantity b plus c equals ab plus ac. So when multiplying a number by a sum, this number can be distributed over each term inside the parentheses. For example, 3 times the quantity. 4 plus 5 equals 3 times. 4 plus 3 times 5. This property is especially important when simplifying algebraic expressions with variables inside the parentheses. For example, 2 times the quantity, x plus 7. While in the example above, we could add 4 plus 5. First, then multiply the result by 3. In this example, we cannot combine together x and 7 instead. To remove the parenthesis, we multiply 2 by x, and again 2 times 7, and 2 times x is 2x, and 2 times 7 is 14. The next property is the identity property of addition. A plus 0 equals a, and 0 plus a is also equal to a. So adding a 0 to a number does not change that number. For example, 6 plus 0 equals 6, and 0 plus 6 is also equal to 6 in both examples. Number 6 maintains its identity. Next is the identity property of multiplication. A times 1 equals a, and 1 times a equals a. So multiplying a number by 1 does not change that number. For example, 4 times 1 equals 4, and 1 times 4 equals 4. The next property is the inverse property of addition a plus minus a equals 0, and minus a plus a is also 0. So the sum of two opposite numbers equals 0. For example, 7 plus minus 7 equals 0, and minus 7 plus 7 is also 0. Next is the inverse property of multiplication. Multiply with 1 by a equals 1. And 1 by a multiply a is also equal to 1. So the product of a non-zero number and its reciprocal equals 1. For example, 8 times 1 by 8 equals 1 because 8 and 8 cancels. 1 by 8 times 8 is also 1. Another example, 2 by 8 5 multiply 5 by 2 equals 1 because 5 cancels and 2 also cancels. And the last property is the multiplication property of 0. Our times 0 equals 0. So a number multiplied by 0 equals 0. For example, 5 times 0 equals 0. So here we have the properties of real numbers. So today we explored how all number types connect under real numbers.
Now I understand natural whole integers, rational real numbers.
Perfect. Next, we'll solve some examples on real numbers. Don't forget to like, share, and subscribe to Gonit Guru.